right, 11.3 is the integral test and the P-series test. So we're going to look at these two. We get two more tests in 11.3, and it turns out that this thing called the P-series is a very natural follow-up to the integral test. So most of our conversation will be about the integral test, and then we're going to see at the end this new thing, kind of a very simple case that we end up calling the P-series. Okay, so here's what we've got at the top. You can see there. It's usually not easy to find a formula for the nth partial sum, capital S sub n. If we cannot find a formula for capital S sub n, we're therefore not going to be able to find what number the series converges to if it does converge. So from here out, we're not going to try and find a formula for the nth partial sum. We're simply going to ask the question, does the series converge or diverge? Okay, so what's the integral test? Let me show you the whole thing, and I'll give you a moment to write that as I read it once over, and then we'll go back and sort of explain what's going on. So it says, let f of x be positive, continuous, and decreasing for x greater than or equal to 1. Then, for a sub n equal to f of n, the series from n equals 1 to infinity of a sub n, and the integral from 1 to infinity f of x dx either both converge or both diverge. Okay, so that's what it says. What is going on here? So when we say a sub n equals f of n, we mean this is a sequence. This is the corresponding function. All right, so whatever the formula for the sequence, we're just going to think of the function, kind of like, with the same formula, if you will. The big difference between a sequence and a function is a function is continuous, right? It's a continuous curve, where a sequence is just these points, either, going up or down, whatever the terms are doing, but the function connects them all with a curve. So there's actually a lot more information in the function than there was in the sequence, but I think you get the idea. Then we're going to say, all right, we no longer call the function with the variable n. We're going to switch back to the more typical x, but it's got the same formula nonetheless. Okay. So then it turns out this series and this integral do the same thing. If this converges, then this converges. If this diverges, then this diverges. Really, the logic we're going to look at will be the opposite. If this converges, then we're going to be able to say this converges. If this integral diverges, then we're going to be able to say this series diverges. One other thing, you notice that we're beginning the series at 1, and you don't have to. This could start anywhere. Could start at 0, could start at 2 or 3 or 4. Okay, we just go with 1 by default again. We also say that the integral begins at 1. Really, same thing. Wherever this begins, that's where we begin the integral. So if this started at 0, we'd start the integral at 0. They just need to match. We also say that back here, that f of x, like the conditions, right? F of x has to be positive, continuous, and decreasing for x greater than or equal to 1. Well, it doesn't have to be 1. It could be anywhere. We just say 1 by default. But whatever that is, then these have to follow. Okay. Last thing about the conditions. So before we can even look at this integral and determine if it converges or diverges, this has to be true. Your function's got to be positive, continuous, and decreasing in order for these to be guaranteed to be able to, whatever this does, this follows. So in all the questions we do, these things have to be checked first, make sure that all of those work out, and then we can look at the integral. and then finally answer about the series. Okay, well, let's get into it. Turns out I've only got 2 examples, and I really think that's all that's necessary because we've done lots of integrals up until this point. That's about all we've done. But okay, let's see how this works. So hey, here our series begins at 2, no problem, 2 to infinity, and the series is the nth term of the series 1 over n square root of natural log n. Interesting series, got a lot going on. Luckily, the question is simply, does it converge or diverge? Okay, so as I just explained, we're going to take the function to be the corresponding, right? So it's the same formula now, but now we're going to use x. And we need to check those 3 conditions on this f of x. Is it positive? Is it continuous? And is it decreasing? Those are the 3. Okay. Well, let's take a look. Is this function positive? And we're only concerned with greater than or equal to 2. Is that always positive if x is greater than or equal to 2? There's really no math to do here. I think we can all see this, and yep, if I plug in 2, that's a positive number, that's a positive number, it'll all be positive. And if I plug in anything bigger than 2, well, it'll still all be positive. There's no math to do there. We're just going to write it so somebody knows that we thought about it. Yes, that function is positive. Maybe I'll write f of x. Be really clear. F of x is positive for x greater than or equal to 2. Check. There's no math to do. We can just observe that. Okay, the next condition is f of x continuous for x greater than or equal to 2. Really, same sort of thing. There's no math to do here. We can visually check that that's the case. So what does that mean? Well, hey, for anything 2 or larger, do we ever divide by 0? Right? Like that would be the issue to break continuity. And nope. You know what though? If x was equal to 1, we'd be dividing by 0, natural log of 1. Luckily, we start at 2. And so we avoid that. Maybe that's the reason why it starts at 2, to avoid dividing by 0 at 1. But if you're 2 or bigger, yep, it's always going to be continuous, no problem. Okay, now the last one is f of x decreasing for x greater than or equal to 2. That's a more difficult question. I can tell that it's always going to be positive, but is it always getting smaller? That's a little bit more difficult. So, you know, that's going to take a little bit more work. I could understand here, though, somebody could look at this and say, yeah, you know what, at 2, well, I don't know what that would be, but then if I raised it to 3, well, the denominator is getting bigger, so it's decreasing, and then at 4, the denominator is getting bigger. You know, and for both x and natural log x, it's always getting bigger and bigger. So the value of f of x is getting smaller. I could see somebody making that argument. Even so, you don't want to trust that people can follow that sort of logic for the decreasing. And oftentimes, you might deceive yourself into thinking that it's simple, and it's actually not decreasing, or it's not that simple. So we are going to do something here. What we're going to do, and my note, we're going to bring it to the next page. There is some math to do. We're going to show that f of x is decreasing, and no one will be able to argue with us if we show that f prime of x is always less than 0 for x greater than or equal to 2. And sorry, that's a little bit blurry, but I think you get what I'm saying. So there is math to do for the decreasing piece. We're going to show the derivative is negative. Okay, let's go for it. So when it comes to this derivative, obviously this is not a lecture on derivatives. So I would encourage you to take this derivative on your own in whatever fashion you see fit, and then kind of come back and compare it with mine. So I use the quotient rule for my derivative and got this. Of course, there's a chain rule and a product rule happening in there. X natural log x, you got that product rule, and then on the natural log, you've got a chain rule happening. I trust that you guys at this point are experts in derivatives, and if you're not, well, it's there on the screen for you too. But I'm not going to talk about that. I'm just going to kind of show you my simplification. So let me hide this for a moment with my eraser. Okay, so I simplified all that. I had a nice times 0 here, and then this was all times -1, and I got it down to this, and I rewrote the natural log to the -1/2 power, and the 1/2, I rewrote it as this fraction. And then we could probably stop right here for our purposes, but I went a step further, and I multiplied the top and the bottom by that denominator to really get it as simplified as possible. And it really cleans up nicely too. And the point is, I got this in the end for my derivative. Okay. So what I got, -2 natural log x minus 1 over 2x squared natural log x square root natural log x. Okay, so at that point, and you can see the rest of my work here, but I'll just kind of speak to this. Once we have the derivative and we've got it as simplified as possible, how can we then show or convince anybody that that derivative really is negative, less than 0, for the values that we like? Okay, so here's a way that no one will be able to argue with. I've kind of got the note here on the far right. We can barely fit everything in. Hey, let's just take x equals 2, all right? If we plug in 2 for all of the x's, would you agree that the numerator will be negative and the denominator will be positive at x equals 2? Sure, I've got a negative there. Natural log of 2 is a positive number. Then I'm going to subtract. This will all be positive. I'll have a negative divided by a positive, so I know it's negative. And then for anything bigger than 2, right? If I plug in 3 or 4 or 5 or 6, it's always going to be a negative over a positive. That's my thinking process to show here the derivative is negative for x greater than or equal to 2. You also realize, hey, if this had started at 1, x equals 1, we'd have a problem. I'd have a 0 there. Well, I'd be dividing by 0 as well. That'd be a bigger problem. So again, you kind of see why we're starting at 2 to make all of this work nicely. Okay, hopefully that makes sense. Obviously, questions on that, bring them to our discussion time. All right, at this point, we have shown that the function is positive, continuous, and decreasing. Now, it's time to actually apply the test. We know that we can apply the test, that our test is something we can use here. So what are we going to do? All right, we're going to look back at our function, 1 over x square root natural log x. We're going to take the integral from 2 to infinity, and if this converges, then we know the series also converges, and if this diverges, then we know the series also diverges. Our task now is simply, can we find that antiderivative? And we notice it's an improper integral, so we'll need to take this limit as t goes to infinity. If we can do that, we've got the answer to the series. All right, so you see, first thing I do, switch it over in the improper integral style, t to infinity. All right. Now we got to think, hey, is it possible to take that antiderivative? And sure is. Maybe you notice, hey, natural log x and a 1 over x. I can do a pretty straightforward u substitution. And I can rewrite this as the limit as t goes to infinity, 2 to t, u to the negative 1/2 du. Okay, okay. We're getting there. We're almost there. Now we take our antiderivative. 2u to the 1/2 from 2 to t. Limit as t goes to infinity. We've almost got it. Put our u back in. Square root natural log x. Plug in your t. Plug in your 2. And what happens? Maybe going a little bit too quickly. Plug in your t. Plug in your 2. Now, what happens as we take the limit as t goes to infinity? Well, the natural log of infinity is infinity. The square root of that, it's all going to infinity here. That's a number, so infinity minus some number is infinity, and we can tell that that integral diverges. Of course, we're not quite done yet. The question originally was not about the integral. It was about the series. Well, hey, if the integral diverges, then the series must follow. That series diverges, and we're going to say by the integral test. We always want to cite the test that we use. That's just the nature of how we go about these, so everybody knows what we did. Okay, well, a lot of steps there, and there's like 2 halves to the problem, right? First half showing that f of x meet those 3 criteria. And then, if that really does work out, then actually taking the integral. And here it was not too bad. Of course, you might get some that require by parts or a trig sub, right? That's all fair game. There you go. We are going to do one more example of the integral test in the next video.